Okay, so if you recall, many moons ago when we last met, we were talking about the chemistry of alkynes. And what I hope you can see, the connection that I hope you can make is that all of these reactions of the alkynes are very, very similar, if not identical, to the reactions of the alkenes. The only difference is that because alkynes have two pi bonds, these reactions happen two times. All right. But all of the reactions that we've seen up to this point have been virtually identical to the reactions of alkenes that you already learned. All right. This is where we stopped last time, and this was the hydration of alkynes. Now, mechanistically, it's identical to the hydration of alkenes, right? You can do this Markovnikov in order to get the OH of the water um, in the Markovnikov position using mercury, just like you did with alkenes. You can do it with boron reagents if you want to get the OH of the water in the anti-Markovnikov position, just like alkenes. The only difference here is that because of the nature of the alkyne, if you put an OH group, you still have a pi bond there, right? And that makes this kind of a special type of molecule that we call an enol. Enols are not stable. They are. It is much preferable, more preferable to have a carbon oxygen double bond than a carbon carbon double bond. And so when you form an enol, it will immediately rearrange the special rearrangement that we call tautomerization to make a carbonyl compound. Mhm. Not particularly. I mean, you'll see it here and there. You'll see it next semester, but it's not terribly important. The main thing is that you know that it is a rearrangement that takes that enolic uh, form into the much more stable carbonyl form. And so, because of the Markovnikov nature of the mercuration, you end up with a ketone as your final product. If you do the hydroboration, because that is anti-Markovnikov addition, you end up making the aldehyde form. All right. Now, one final note I want to make on this. When you're doing boration, the hydroboration of the alkyne, people don't usually use BH3, this borane. They don't typically do that because borane has multiple hydrogens. So this could potentially add a couple of times. And so what people will generally do is they will use these larger, more hindered boron reagents that have only one hydrogen. And the two most common for this is this compound called 9-BBN or this compound that's abbreviated Thia2BH, it's dithiamyl borane. I'm going to go ahead and show you what the structures look like. I'm never going to ask you for this on an exam, but just so you can see what these are more than just a mishmash of letters. 9-BBN looks like this. So it's this large bicyclic compound. The dicyamyl borane looks like this. So again, not that you need to know the structures of these, but only to know that they are both very, very large hindered boron compounds that can deliver only one hydrogen. Okay. So again, only know this just, I mean, just to recognize the names. If you ever see a 9-BBN or that dithiamyl borane uh, compound, it's just all you need to know is that these are the ones that are used to hydrate alkynes. Okay. Okay. So we have almost finished talking about. Actually, could you give the product of that reaction? So this is obviously a mercuration. That is going to be a Markovnikov addition of the water. And so we would get that as your initial product. Now that, of course, is the enol, which will then rearrange to make the ketone. All right, any questions here? Okay, so the last reaction that we have of the alkynes is the oxidative cleavage. So we saw, again, same stuff over and over again as with the alkenes. We saw oxidative cleavage with the alkenes. You can also do this with alkynes. In fact, with alkynes, it's even easier. Because if you'll remember, there were two ways we had of cleaving the alkenes in an oxidative manner. We could do ozonolysis, or we could use permanganate hot and concentrated. The ozonolysis is the milder form. The permanganate is the more vigorous form. And so if you recall, with ozonolysis and alkenes, what we isolated were ketones and aldehydes. All right, that was the milder form. With the more strongly oxidizing conditions, we isolated ketones, but we couldn't isolate aldehydes in these very strong oxidizing conditions because the aldehydes can oxidize further to give carboxylic acids. All right, so there was a difference. There's a difference in product mixture depending on whether you use the milder ozonolysis or the more strong permanganate oxidation. The nice thing about alkynes is there is no difference. With alkynes, you're going to isolate only carboxylic acids. You're going to get a pair of carboxylic acids, whether you do this with ozonolysis or whether you do this with permanganate. It's all the same. So let's have a look. Let's look at some specific examples. Let's do this reaction here. So you can see we're taking that alkyne and we are treating it with ozonolysis conditions. Now, just as with alkenes, what's going to happen is you're going to split the molecule in two at the multiple bond. Now, again, as I just mentioned, you are going to get only carboxylic acid from this. So if I split that alkyne in two, I should get two separate carboxylic acid products. And really all you need to do is count your carbons. So over on the left-hand side of the split, I have 1, 2, 3 carbons. So that means I should get a 3-carbon carboxylic acid. On the right of the split, I have a 1, 2. I've got 1, 2 carbons. So then I should also end up with a 2-carbon carboxylic acid. All right. Down below, I have the exact same compound. We're just cleaving with permanganate here. You'll note the similarity. We're going to, again, cut the molecule at the multiple bond. To the left of the split, I have a 3-carbon group. So we make a 3-carbon carboxylic acid. Right of the split, I've got two carbons. So we end up also with a two carbon carboxylic acid. The exact same product as we got with ozonology. Any questions there? All right, let's look at maybe one final reaction. What if I were to ask you about this? Could you give me the product of that ozonology? Well, here again, all we're going to do is we're going to split the molecule in two at the triple bond. So left of the split, I have the ring and one carbon outside. And then right of the split, I have a one, two, three. I've got a four carbon chain. So we should end up with that. All right. Questions on that? All right. Well, that takes us to the end of alkyne reaction. So again, if you can, I think alkynes are pretty, if you know the alkene reactions, I think the alkyne reactions will be pretty straightforward for you because they are nearly identical. Okay. All right. Let's go ahead and jump over, switch gears a little bit and get into the reactions of alcohol. Now, again, I'm going to address the physical properties and reactivity in lab today. I'll talk about nomenclature of alcohols in lab on Thursday. I'm going to just jump into synthesis, touch a little bit on synthesis, and then we'll spend the rest of the day talking about reactions of alcohols. Okay. I don't want to spend too much time on the synthesis of these because you actually know all the ways of synthesizing alcohols at this point. Okay, that was the subject of most of those alkene reactions. All right. But I do want to spend a little bit of time talking about this first method because we didn't talk about this explicitly. I think we kind of just indirectly talked about this. But one of the ways we can make alcohols is through the SN2 displacement with hydroxide ions. So imagine if I were to take this bromopropane and I were to treat it with hydroxide, well, you'll recall hydroxide is a strong nucleophile, strong base. We have a primary alkyl halide, and so this will undergo direct SN2. Hydroxide attacks, kicks out the good leaving group. And voila, you have an alcohol. It is alcohol, reactions of alcohol. Make sure that I published it. You got it? Okay, cool. Um, so you can, this is an efficient way of making alcohol only if your substrate is primary or methyl. Okay, remember, this is an SN2 reaction. So it will only work well if your substrate is primary or methyl. What do you think is going to happen here? So notice I've got pretty much the exact same reaction. The only difference is instead of a primary alkyl halide, I'm trying to do this on a secondary alkyl halide. Yeah, the problem here is that you would make some of the desired alcohol, some of the SN2, but with secondary halides, you're going to run into some pretty stiff competition with the E2 mechanism, right? Because remember, again, hydroxide is both strong nucleophile and strong base. And so this could just as easily come in and grab the adjacent proton and kick out the halide that way, giving you the E2 product. And in fact, when you have these secondary halides, the E2 predominates by kind of a lot, actually. I'll give you some data on this. You'd see about 85% E2 here. But not a great way of making alcohol. So the bottom line is you can do this direct SN2 displacement if and only if you have methyl or primary halide. Secondary is going to give you a mix, but it will lean towards E2. And certainly, obviously, if you had a tertiary halide, you'd get exclusively E2. Okay, questions on that? Okay. I have compiled these other methods of synthesis and put them into the slides, but I'm not going to spend any time on this because we've already talked about it all. You can make alcohols through hydration of alkene, right? You already know this. Acid catalyzed, oxymercuration, hydroboration. Old news. You can make alcohols through thin dihydroxylation of alkene. You can get diol. Again, reaction we've seen before, old news. You can make alcohol through halohydrin. You can make alcohols through the addition of an alkyne to a carbonyl compound. Again, we've seen that before. Actually, just as a means of review, could you predict the product of that reaction? Actually, the way I should write this to be a little bit more correct. That would be the better way of writing that. What is the NaNH2 going to do in this case? What is the point of the NaNH2? NaNH2 is a very specialized base, and it's almost exclusively used to deprotonate terminal alkynes. So that will generate that nucleophilic acetylide, which can then go and attack the carbonyl carbon. That would be the initial addition product. In step three, it shows you add acid, and the reason for that is to protonate the resulting alkoxide. That would be the alcohol product. Now, again, as you're getting used to these reactions, I encourage you to count carbon. Your acetylide has 1, 2, 3, 4, 5, 6 carbons. You're adding it to something that has 1, 2, 3, 4 carbons. 6 plus 4 is 10. My product better have 10 carbons or I need to redo it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think we're good. All right, questions here. Okay, what we're going to spend um, a good chunk of today talking about is something we've already at least introduced. And this is the very famous Grignard reaction. Now, the point of the Grignard reaction is it is an organometallic reaction, meaning it has a organic side and it also involves a metal. In the case of the Grignard reaction, magnesium. I'm going to introduce this at the same time as we talk about this second category called organolithium reactions. And the reason I'm going to do it kind of simultaneously is because mechanistically they are nearly identical to each other. Those metals do exactly the same thing. And what they do is they insert. They insert between the carbon and the halogen of the alkyl halide. Right? And so we looked at this a little bit in lab when we were talking about when we were doing the Grignard reaction. Remember, the point of the magnesium is that it inserts and then it reverses the polarity at that carbon. When the bromine was attached to it, because the halogen is very electronegative, that makes the carbon here very delta positive. However, when the magnesium adds in, remember, metals are very, very electropositive. Because that is such a positive species attached to the carbon, that now reverses the polarity of the carbon and makes it very, very delta negative. In fact, so it becomes so delta negative, we very commonly will just treat it as a carbanion because that is how it behaves. And you can do this with lithium as well. And you get essentially the exact same thing. But both of these become carbanions, essentially. And so what we're going to do with these carbanion type species is we are going to add them to carbonyl compounds, specifically aldehydes and ketones. And why this is so important, I would say this is going to be the most important reaction for quite a while in your organic chemistry careers. And the reason why this is such an important reaction is because it is the first and most common carbon-carbon bond forming reaction. I mean, you think about it as organic chemists, kind of by definition, what we're trying to do is build organic molecules. Well, if you're going to be constructing organic molecules, you have to be able to make carbon-carbon bonds. Well, it turns out that's not a lot of times that's easier said than done. It is quite difficult to make carbon-carbon bonds. And usually, historically, when you discover a new way of making carbon-carbon bonds, you end up getting a Nobel Prize for it. And this is the story for French chemist Victor Grignard. He was awarded the Nobel Prize for this reaction in the 1920s, I believe. But in any case, let's go ahead and see what this is going to look like. So you can use the Grignard reaction or alkylithium to make any type of an alcohol you want. You can use the Grignard reaction to make primary alcohols, you can use it to make secondary alcohols, and you can use it to make tertiary alcohols. So let's have a look at this first reaction. So what I'm showing you here is we're going to try to make primary alcohol. So you can see that I'm starting with 2-bromopropane. And as with any Grignard reaction, we're going to add magnesium to it. Now, what that is going to end up looking like or behaving like is that. Essentially, you put a negative charge where the halide was. And that is your nucleophile. Then you're going to come back and you're going to add some carbonyl to it, some electrophile to it. Remember what we talked about when we introduced this in lab. The only thing you need to know about carbonyl chemistry is that the carbonyl carbon is very electropositive. And as a result, nucleophiles, all manner of nucleophiles, love to attack it. So that's what happens. Draw our arrows. The negative charge of the Grignard reagent is going to be attracted and come in and attack the carbon of the carbonyl. Now, I can't just stick a new bond to that carbonyl carbon and leave everything else as is. Because if I did, then this carbon would end up with 5 bonds, which we know can't happen. So as the Grignard reagent comes in to attack, one of the existing bonds has to break. And you can probably guess which one it's going to be. Pi bonds are weaker than sigma bonds, and so the pi bond breaks. That's going to result in a species, in this case, that looks like this. You know, really, if you think about it, this mechanistically is very similar to the reaction we just saw, the acetylide ion coming in to attack carbon. You end up making this alkoxide intermediate, and this thing is just going to hang out until you give it a proton. You'll recall when we did this in lab, you took that gray dishwater looking stuff and you dumped it into the sulfuric acid, right? We have to give this acid in order to give that thing a proton. So that's why anytime you see a Grignard reaction written out, there will always be, step 1, the magnesium, blah, 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 blah. Step 2, H+. There will always be an acidification step because you have to provide that O-, its proton, if you want to isolate a neutral organic molecule. But the bottom line, if you add a Grignard reagent to formaldehyde, what this compound is, you will make a primary alcohol. Now, there is another way of getting primary alcohol. The other way of getting primary alcohols is by adding the Grignard reagent to this thing. Kind of a weird looking thing. Three-membered cyclic ether. It has a few, it goes by a few names. Um, I usually call this ethylene oxide. But you might see it called epoxide or oxirane. Has a few names. Oxycyclopropane is another one. But the bottom line is this thing is highly reactive. Somebody can you imagine why that would be? What would make that such a reactive electrophile? Yeah, exactly. I mean, that thing's got 60-degree bond angle. It's exceptionally strained. And so it will do anything to pop open to lose all of that ring strain. And so you'll see next semester when you study this chemistry in detail, um, ethylene oxide will react with all manner of nucleophiles, and certainly with something as strongly nucleophilic as a carbanion. And so what's going to happen here is the granular reagent is going to come in and attack one of those carbons, and the thing's going to pop open. And it gives you that O minus species again. And that, again, like the case before, is just going to hang out until you give it some acid. And when you do, the resulting product is another primary alcohol. So both of these reactions result in a primary alcohol. The only thing you have to be aware of is that if you do this reaction with formaldehyde, formaldehyde has only one carbon. So you'll note in that reaction, the nucleophile had three carbons, the electrophile had one carbon, and so our product ended up as a four-carbon alcohol. With ethylene oxide, though, your electrophile here has two carbons. So in this case, your product is going to be five carbons in total. Okay, just that's something sometimes people forget is that if they're using ethylene oxide, you are extending your carbon chain by two. All right, questions there? Okay, so we've looked at how you can make a primary alcohol using Grignard chemistry. You can do that by adding the electrophile formaldehyde or the electrophile ethylene oxide. How do you get secondary alcohol? The way you're going to get a secondary alcohol is by adding your Grignard reagent to what I'll call a normal aldehyde. Okay, so in this example, I've got my alkyl halide. I'm going to add magnesium to it. That's going to do the metal insertion and generate a carbanion-like nucleophile that looks like this. Again, the negative charge just ends up where the halide was. Then if I give that a normal type aldehyde, mechanistically, it's all the same. That carbanion is just going to go in and attack the carbonyl carbon. The pi bond breaks, and we end up with an alkoxide intermediate. Mm-hmm. if you're not asked for the mechanism, you don't need to show the any of the middle steps. You could simply take the starting materials and draw in the product. Hmm. Hmm. Yeah. So the difference, so formaldehyde is a one carbon aldehyde. When I say a normal aldehyde, it's going to be an aldehyde connected to some type of other carbon or carbons. Okay? So that's why I say with formaldehyde, you're only extending the carbon chain by one carbon because that's all that formaldehyde has. Okay. Um, okay. So this, like all the ones we've seen before, this alkoxide intermediate is just going to hang out until you give it some acid. And once you do, that will protonate the alkoxide, and then that results in the secondary alcohol. Have a look at this problem. What if I asked you to make that? Could you do that? By the way, any Grignard reaction can be done in minimum two different ways. There are two possibilities of how to synthesize this compound. Now, the thing to remember is the carbon that's holding on to the OH, the carbonyl, used to be a carbonyl. So that means you're going to split this. The disconnection you're going to, there are actually two possibilities for the disconnection. We could disconnect on either side of the carbonyl. I could break it like this, or I could break it like that. So think about what remember, the carbonyl, the piece that holds the carbonyl used to be the carbonyl, used to be the C double bond O. So if I make the green disconnection, by the way, that arrow is a special arrow. We organic chemists are rather fanatical about our arrows. That green arrow right there, that is what is known as a retrosynthesis arrow. What that means is this thing came from these things. It's like a revert, going in reverse. So I could make that secondary alcohol product by combining, remember, the carbonyl used to be the carbonyl. That's not right. I'm going to just do this one at a time. If I do that green disconnection, carbonyl used to be the carbonyl. So that would be the carbonyl piece. There's only two pieces to a Grignard reaction. There's the carbonyl piece and there's the alkyl halide piece. So I'm showing, we split this because the carbonyl used to be the carbonyl. So I've got my carbonyl piece. So the other piece, this 3-carbon piece, would have to be the alkyl halide piece. So those would be two options, or the two pieces. Do you see what the other option would be here for starting material? I could get rid of that disconnection. What if I said we could also do that disconnection? So the carbonyl used to be the carbonyl, so the carbonyl piece using the red disconnection would look like that. So it's kind of the right-hand half of the molecule. And then got your carbonyl piece, then the other piece must be the alkyl halide piece. In this case, it's the ring. Both of those would make the desired product. All right, questions here? All right, yeah, go ahead. No, most of the time it will just say provide a synthesis for this alcohol. And so either one would be perfectly fine. All right, we've seen how to make primary alcohols. We've looked at how to make secondary. Let's do tertiary. So I'm switching it up a little bit. This time I'm using an alkyl lithium just to demonstrate the similarity. So in this case, I've got my, in this case, aryl halide. That works too. I'm going to add lithium. Same kind of idea, right? Wherever you see the halogen, that is where the negative charge develops. So we're going to make this benzene type anion, and it will, like all the cases before, be attracted to the carbonyl carbon. Only this time, look at the carbonyl. This time the carbonyl we're using is not an aldehyde, but rather a ketone. But in terms of mechanism, it's exactly the same. We'd get an alkoxide intermediate that looks like that. And then upon protonation, you get the tertiary alcohol. So it's really just the difference here is what are you adding the Grignard reagent to? You add it to formaldehyde or ethylene oxide, you make a primary alcohol. If you add it to a regular aldehyde, you get a secondary alcohol. If you add it to a ketone, you get a tertiary alcohol. All right. Questions on this? Okay. One last example before we move on. Could you come up with a way of making this alcohol? Now, by the way, what kind of alcohol is this? Is this a primary, secondary, or tertiary alcohol? It's tertiary, so that tells you what your electrophile has to be. Your electrophile here is going to have to be a ketone. And I think there are three possibilities here. All right. Yeah, it really doesn't. So you would have any of these three reactant pairs, and you would add either magnesium or lithium to them. Anybody have questions on these three possibilities? Mhm. So each of these three would end up giving you the desired tertiary alcohol. So that's a lot. That's pretty similar to what your Grignard homework is. It's going to ask you, it'll give you a couple predict the products. Here's a alkyl halide and a carbonyl. What alcohol product would result? And then there's a couple questions that say, here's the target. Give two ways of synthesizing it. Okay. Okay. Now, the Grignard is great, but there are some significant limitations you should be aware of. First and foremost, this is the most common pitfall that I see when people try to use Grignard reactions in their synthesis, especially. The Grignard is a carbanion, and a carbanion is about the strongest nucleophile and strongest base that we have. And as a result, anything that looks remotely acidic will kill your Grignard reagent. That's why, you think back to when we did this in lab, you'll recall that I had you wash all of your glassware ahead of time, put it in the oven for a couple of days, and we were extremely concerned with the 100% complete exclusion of water. Because if water was around, The Grignard reagent, being so basic, would simply go and grab a proton from the water, and then that kills the Grignard reagent. Well, anything in your molecule can do that as well. Anything that is remotely acidic. And when I say remotely acidic, what I'm really kind of talking about here is anything that is heteroatom H. You think about what that means in a functional group sense. There are a lot of functional groups that have heteroatom H. This means you can't do a Grignard reaction when your molecule possesses an alcohol. Certainly not a carboxylic acid. Amines, amides, thiols. Those are probably the biggest concerns. The other issue is you cannot do this if your molecule has multiple bonds with a difference in electronegativity. So what would that be? Well, if you have any other CO double bond. All right, so you wouldn't want to do this reaction if you had an aldehyde and a ketone in your molecule. You can't do this if your molecule possesses a CN triple bond because it's a multiple bond where the two things have a difference in electronegativity. You can't do it if your molecule possesses a CN double bond. You can't do this if your molecule possesses an NO2. You cannot have multiple bonds where there's a difference in electronegativity of the bonded atom. I mean, you think about it, that's why the Grignard reaction works to begin with, because your carbon has a delta plus that the Grignard reagent wants to attack. Well, that also has a delta plus. It's a pi bond with a delta plus. That's also a pi bond with a delta plus. So where this comes an issue is something like, got a couple bad examples of Grignard reactions here. The top one would work just fine. You can probably predict the product of that on your own. You see the problem with this reaction. So presumably what this person is trying to do is make the Grignard reagent here and have that go and attack the ethylene oxide. To make that as your product. What's the problem with doing that? By the way, this reaction will not work. So you take the alkyl. So as soon as you make the carbanion here, before you could even get this electrophile into the flask, this carbanion would see the carbonyl of another molecule and go and attack it. The problem with this reaction as written is you have a reaction where you have two electrophiles in it. This electrophile that you want it to react with, yet you have another electrophile there. With these Grignard reactions, you only want to have one nucleophile and one electrophile in the flask. Otherwise, things get really messy. What's the problem in the second example? Mm-hmm. It would be very unpredictable. It'd be very messy. So nobody would ever do that. I mean, you might be able to isolate some of what you wanted in like, I don't know, a handful of a percent yield, but you would also spend an inordinate amount of time cleaning up that mess to even isolate that small percentage of product. Mm-hmm. I would just write X. Yeah, it's you would never do a reaction like that. What's the problem here? Yeah, exactly. So presumably what this person is trying to do is create a Grignard reagent out of the ring and have it attack the aldehyde. However, as we just discussed, you have an OH here. You have a heteroatom H. So before you could even have the Grignard attack the aldehyde, it's going to see that acidic proton and just go and do a proton transfer, and then the reaction is over. All right. Another, let me show you one last one. Something else that would be a problem would be this. Do you see the problem there? Kind of similar to that first example. Yeah, I've got two carbonyls. I have here again two electrophiles. You only want to do Grignard reactions where you have one designated nucleophile and one designated electrophile. All right. Any questions here? All right. I know we spent quite a bit of time talking about this reaction, but that just goes to show how important it is. And again, you're going to get more practice with this from the homework due for Thursday. Okay. But at this point, I think we can go ahead and move on. And we're going to move on to some redox chemistry. And I want to show you, I'm going to just kind of show you some general features of alcohol redox, and then we'll look at specifics. So notice what I have in this first sequence. I am taking a primary alcohol, and this O in brackets, all that means is just some generic oxidizing agent. We'll flesh that out later. But if you take a primary alcohol and oxidize it. Now, by the way, before we actually do that, you've all done redox chemistry before. You spent probably a good chunk of time in Gen Chem doing redox. And you probably learned something like, what are those acronyms? Oil rig, I think was one. Leo the lion says grr. There's a bunch of them, but the point is you probably learned about redox chemistry using electrons as the currency. Loss of electrons is oxidation, gain of electrons is reduction. We don't really view redox chemistry in the same way in OChem. In organic, what we look at is oxygens and hydrogens. So it should probably make good sense to you. If you're gaining oxygens, well, that's an oxidation. But the other way you can look at this is through the hydrogen lens. If you are gaining hydrogens, that's a reduction. Or if you're losing hydrogens, that's also an oxidation. So we can kind of look at it through this oxygen-hydrogen view. So if I have that primary alcohol shown and I oxidize it, an oxidized form of that would be this. To turn it into the aldehyde. Can you recognize the aldehyde as being more highly oxidized than the primary alcohol? Well, one easy way to do is just look at the carbonyl that becomes the carbonyl and look at how many hydrogens you have. Here we've got 2 hydrogens. Here there's only 1. We've lost hydrogen in going from the alcohol to the aldehyde. You can also kind of think of it from the viewpoint of the oxygen. This has 1 bond to oxygen. This has 2 bonds to oxygen. So the aldehyde is more oxidized than the alcohol. Mm-hmm. Yes. But the other way, sometimes I think it's easier to just look at the hydrogen. Here we've got 2 hydrogens. Here we've only got 1. A loss of hydrogen is also oxidation. Now, we can oxidize that aldehyde even further. You can oxidize the aldehyde up to the carboxylic acid. Can you recognize that as an oxidation? The aldehyde has 1 oxygen on the carbon. The carboxylic acid has 2 oxygens on the carbon. Now, if you can go in one direction, you can also go in the opposite direction. Right? This is something that's known as the principle of microscopic reversibility. If I can take a primary alcohol and oxidize it all the way up to the carboxylic acid, I must also be able to take a carboxylic acid and then reduce it down to the primary alcohol. So if I take that carboxylic acid shown in that second row, and I add this bracket R, that's just some generic reducing agent, I add some reducing agent, I am going to be able to reduce the carboxylic acid to the aldehyde. And then I can reduce that even further. to the primary alcohol. Exact same sequence, exact same intermediate. We're just going in one direction and then going in the opposite direction. Look what happens though if you start with a secondary alcohol. Story's going to be a little bit different. Because note, whereas the primary alcohol started with two hydrogens, the secondary alcohol only has one. So if I oxidize a secondary alcohol, we're going to lose that hydrogen and generate a ketone. You see the difference between the oxidation of the primary compared to the oxidation of the secondary. That primary alcohol, once you oxidized it to the aldehyde, there was still a hydrogen there that you could lose to do a second oxidation step. When oxidizing the secondary alcohol, I'm going to get to a ketone, but now I don't have any more hydrogen to lose. So there's no way of oxidizing that further. So with a secondary alcohol, you can oxidize them, but only one step. Oxidize it to the ketone, and then you're stuck. Look at the bottom there. Got the oxidation of the tertiary alcohol. What do you think happens here? Well, the primary alcohol had two hydrogens on it, so we could oxidize it two stages. The secondary alcohol has one hydrogen on it, so we could oxidize it one stage. The tertiary alcohol has no hydrogens on it. And thus, nothing happens. Tertiary alcohols cannot be oxidized. Questions here? All right. So that is just kind of the alcohol redox chemistry in a nutshell. What I want to do now is talk some specifics. We'll look at reduction first. There are two broad ways of reducing aldehydes and ketones. And the first one you kind of already know. You know, we talked about catalytic hydrogenation before. We talked about that in the context of reducing alkenes. We talked about using catalytic hydrogenation to reduce alkynes. Turns out you can also reduce carbonyls this way, and in the exact same mechanistic style. So you'll recall that when we talked about the reduction of alkenes and alkynes, we said you're going to have some kind of a metal catalyst whose job it was to adsorb hydrogen. And then what happened was the CC double bond or the CC triple bond came and kind of sat down on that bed of hydrogen. And then the hydrogens got transferred, right? One hydrogen added to one of the double bond carbons and another hydrogen added to the other. Well, mechanistically, the exact same thing is going to happen here. The only difference is instead of adding to a CC double bond, it's a CO double bond. And so the end product here, if you kind of draw that out, that member of the double bond got a hydrogen, and so did that member. So the result of the reduction of that carbonyl ends up giving you an alcohol as product. Now you can see that I've got the showing you what happens if you reduce an aldehyde compared to what happens if you reduce the ketone. Mechanistically, it's the exact same thing. The only difference is in the type of alcohol product you get. If you're starting with an aldehyde and you reduce that, you're going to make a primary alcohol. If you start with a ketone and reduce that, you're going to end up getting a secondary alcohol. Now, the only difference here that you can really recognize with the catalytic hydrogenation of these carbonyls compared to the alkenes and alkynes is in the catalyst. The catalyst used, back when we did alkyne and alkenes, the catalyst was usually platinum and palladium. With trying to reduce carbonyls are stronger bonds and they require more active catalyst. And so what you typically see if you're trying to reduce a carbonyl with catalytic hydrogenation, what they tend to use more often than not is something that's called rainy nickel. And rainy nickel is actually just a nickel aluminum alloy. This is a more active catalyst. All right. Have a look at this one. It's a pretty straightforward example. Could you predict the hydrogenation product of this? Hydrogenation of butanone. So they're usually not too terrible. Again, just like with the hydrogenation of the alkenes and alkynes, you just need to add a hydrogen to each of the double bond members. So I added a hydrogen to the double bond carbon, and I added a hydrogen to the double bond oxygen. And we started with a ketone, and you end up with a secondary alcohol. What about this next example? What do you think? Are we going to be able to reduce the benzene ring under these conditions? No, you couldn't do that with catalytic hydrogenation with platinum and palladium. You certainly can't do it with rainy nickel either. So the benzene is going to remain intact. Okay, so we're using rainy nickel, so that is going to certainly reduce the aldehyde. What about the alkene? Do we keep the double bond, the carbon-carbon double bond, or do we reduce that? Well, remember, carbonyls are harder to reduce than CC double bond. So if you're using conditions that are sufficient to reduce the carbonyl, they will certainly be strong enough to reduce a regular CC double bond. So no, I am not going to leave the double bond. The carbonyl and the CC double bond will be reduced under these conditions. All right. Questions here? Okay, I think that's probably a good place to stop.